Hello, this is Professor Khan and we are in week 3 EST-204 heat system design, and this week we'll talk about energy and building shell. So last week we talked about energy, forms of energy, and I hope those concepts got solidified with you so we can carry on with these concepts as we go along trying to design a heating system. So we'll talk about identifying and locating a building shell. What is a building shell? And probably have an idea already. It's basically putting the house or a building in an envelope and trying to use that as your calculation method. Recognizing the construction material and supplies, which is very vital to heating and cooling applications. We also will talk about the basis of transmission losses. So there are two types of heat loss that I want you to remember, please, which are heat loss, two types. One of them is transmission, and the other one is infiltration, which is also known as air leaks. So we'll talk about that as well, and we'll talk about the transmission losses from walls and windows and doors. Moving on. So again, two types: transmission and infiltration. What is transmission? Transmission is heat loss or heat movement through walls, through windows and doors. Infiltration is the air leaking from the house to the outside, from the outside to the inside as well. What is fenestration? Fenestration is a fancy word for doors and windows. So when you have fenestration, probably this means the doors and windows in that house. Usually with fenestration we have less issues than windows because we do not open doors and windows as often. So that is something to consider. So we have losses from transmission, that's from walls, from doors and windows. We have also infiltration, that's through cracks in the walls, through windows, leakage, and also we have a lot of loss from fenestration, which is a combination between transmission and infiltration. We'll talk about that again. We'll dedicate a whole week for doors and windows and how do we counteract the heat loss through doors and windows. So building shell, if you look at we said before, the second law of thermodynamics is that heat moves from hot to cold. So in the winter we will lose heat from inside to outside, so there's a heat loss from the house to the outside. And if you look here, this is heat loss in the winter. You lose heat through air leakage, through transmission, through walls, and through the ceiling. So you supply heat from your system, but this is how you lose, and you want to have these to be equal so you can maintain your comfort zone. In the summertime you have heat gain, solar heat, air leakage gain, internal heat from bodies, from equipment, and you also have from transmission, and you're trying to remove heat from the system in order to achieve comfort. So that's the building shell is, and the envelope where the home is located, and how you want it to maintain, how do you want the dwelling or the house to maintain the comfort. And we said human comfort is between 65 to 85, and actually maybe 80, and relative humidity is 40 to 60. Okay, insulation and heat transmission. So this is very important. We're talking about insulation and how would that affect our heat transmission from inside and outside. And if we look here, this is a wall that is empty, okay, and this cavity in here is exerting some radiation through the space, and also there's air moving inside, so there's a lot of heat transmission through this vacuum of a wall, through radiation, also through the air circulating around the wall. So an empty wall, even though air is insulating, is not again an absolute insulator, and it does move and keep transmitting heat, so you lose heat through an empty wall. What if you have a solid wall? That's also conduction. We said conduction is also very powerful means. If you have solid wall with wood, probably you have a lot of conduction. But if you have insulation, you are kind of mitigating or slowing down the heat transmission. So the area here is the heat loss and heat transmission through that wall. That's why insulation is very important, and the type of insulation also is very important. What a good thermos do? What do I mean by this question? If you think of when you buy a thermos and you think of what is it doing to keep the liquid inside it very hot, or if you want to keep it cool for the longest period possible, you will see that the walls of the thermos has foam insulation, and some of them have also vacuum. And also, if you look inside, it has a reflective surface. The reflective surface, actually, this will counteract radiation, heat loss, and the vacuum will eliminate convection because there is no air inside, and the foam can mitigate or reduce heat loss through conduction. So this is for conduction, and a lot of companies are trying to compete of having the best thermos, and by doing the best they can with those three heat transfer means. And also, when do you lose heat in a thermos? Usually when you open it or when you place it on a top, so you lose heat from the bottom. Also when you open it, you have a lot of convection and vapor coming out, and you also bring in outside air in. So think of a thermos and try to extrapolate that into a house. So we'll talk a little bit about the basics of heat transmission. So heat transmission has the symbol of Q. So Q for us is heat transmission rate. It's called the heat transfer rate, and this formula is going to be with us till next semester. So the transmission of heat through a surface or through a medium depends a lot on the area, the thermal conductivity of the material. We're not going to use that now. We have something else that we can look up directly, and delta T. So remember this formula. It's going to be with you for a long time. I will repeat that a lot, but this is the basis for heat transmission. So it goes through the wall, heat goes through walls. It depends on the thickness of the wall, it depends on the area of the wall, the material, and delta T. So delta T in this example is the difference of temperature between inside and outside. The K factor is the thermal conductivity of the air and how thick the wall is, and the area. I will try to summarize that again to make it not as complicated, but I would like to explain a little bit. We know the thickness of the wall. We know how large the wall is, that surface area, inches square, and we know the temperature inside and outside. That's something you can measure. K is the thermal conductivity, is a property of the material itself. We are not going to look into that too much, but I would look to explain what is the relationship of the material thermal conductivity. And again, you don't have to remember this. This is just to help you understand. This is the rate of heat loss. Somebody at some point was able to calculate this thermal conductivity of the material doing a lot of experimentation, and it's the BTU, which is the quantity of heat going per hour, foot square per temperature. That's in imperial units, and this is in metrics unit, in SI. Kilowatt meter square and temperature. So the BTU hour, that's energy rate. Foot square is the area, and degree Fahrenheit is the delta T. So again, we're going to Q equal area times K times delta T. We still did not cover the K part, so we know what the delta T is and we know what the area is. So for example, how do we calculate the wall area? Just to touch base on the area, if you have a wall that is 10 feet wide, 8 feet high, and has a window that's 4 by 4, what is the area of the wall? So now this is my wall. It has a window, and I would like to calculate the heat loss through the wall only, not the window, because again, you probably have figured that the window and the wall are different material. So what I would do is I will get the area of the wall, which is 10 times 8, which is 80. Then I will subtract the area of the window, which is 16. So 80 minus 16, which is 4 by 4, area equal 4 times 4, which is 16, and that will give me 64 foot square. So this, I'm just trying to get you to understand that the area, when we do that heat loss, it's pertaining to a specific material, and this is one step to calculate the wall area. Here it's 70 degree inside, and the outside is 20, so delta T in here is 70 minus 20, which equal 50 degrees Fahrenheit. Thermal conductivity, again, just to help you understand how it is calculated, but we will use something else. I'm going to again, thermal conductivity is added by the wall. It's given usually per inch square and also per width. I'll try not to elaborate too much, but what we are looking for is the R value, which is total resistance of that wall. That's what I want you to remember. And again, this is the relationship of thermal conductivity based on the thickness. You can see that the amount of heat that goes through the wall, it gets less as we have the wall get thicker. Okay, we are not going to do that. We will look the wall and we'll find the resistance, which is the total resistance of the wall regardless of the material, because again, this could be made of different materials and has different K values. It requires a little bit more elaborate math. I'm not going to go into it. But, so these are the thermal conductivity as a physical property for a lot of material. As you can see, aluminum conduct much higher than air. So you see the thermal conductivity, the K value goes up and down as we change the material, and we said like metals usually are very conductive. So all that being said, this is the K value given, and we will go and find the R value. That's something you look up. It will be provided, and it's the K factor times the thickness, which is the conductivity. So this is something you look up in the book. You'll find it in your H22 book. It's a lookup. And the other thing is called the U factor. So to get the right calculation for your equation, you will need the U factor. So I need to remember that the U factor is the inverse of resistance. Where do you get that? You look it up, and the inverse is U. All of this to make the formula that we saw before looks a little bit easier and more user-friendly. So the heat loss for that wall will be heat loss equals area times U times delta T. So here it will be 80 times 20.25 times 50. And I will try to do the math for this. For here, 80 times 0.25 times 50, and I get 1000 BTU per hour. Okay, moving on. So we have a wall made out of brick wall with R value. Now we have the R value, we don't have the U. So what are we gonna do? We're gonna get U equal 1 over R. Temperature inside is 70, outside is 20. The wall is 12 feet by 8. There's a window. It has also an R value. So it's going to be a little bit of a buildup. So calculate the heat transfer through the entire wall. So this is as complicated as it gets to do heat loss. I know it's a little bit involved, but I will walk you through it step by step. So the first step, you set up the total heat loss equation, which we said we're going to get the heat loss through the wall, which is here, and the heat loss through the window. We start with the heat loss through the wall. First step, here you go. Q wall area times U factor times delta T. So to find the area of the wall, you're going to multiply 8 times 12 and subtract window. This is the window, and that will give you 80 feet square, and that's the area of the wall. Let me know if that doesn't make sense. Send me a question through the discussion board. The U for the wall, we said U is 1 over R. We were provided with the R, so we will try to get the U factor. So the resistance for the wall, it has insulation in it. So I'm going to add both insulations together and get the total resistance. And then once I get that, I will divide 1 over the total resistance, and this will be my U factor. Temperature inside, delta T will be the temperature inside minus the temperature outside, which is 50 degrees. If it was the other way around and you get minus, then probably it's going to be cooling and the heat will be gained more than lost. Okay, moving on. Step 3, we'll fill in the blank in the equation. We get the area, we get the U factor, we get the delta T, and this is my BTU per hour. Find out the heat loss for 12 hours, you multiply that by 12. We have to do the same thing for the window, which is calculate the area of the window, 16 foot. U for the window, 1 over R. The R was giving. The U for the window as well is 1 over R, so 0.285. Delta T is going to be the same, and this is the heat loss through the window. So we get the heat loss through the wall, the heat loss through the window, and this is going to be my heat loss for the entire wall, including the window. This is the heat loss from that wall. And usually we do the heat loss for the walls to the outside. Walls to the inside, there is no heat exchange because probably they are the same temperature. So for 12 hours, you multiply that by 12 and you get the total BTU that is required for 12 hours. I know it's a little bit involved, but try to think of the steps slowly, one by one. And what else do I need to say here? Thinking back to the equation, like area times U times delta T. If there is no delta T, what happens? It's 0. The whole thing becomes 0. Makes sense? That's why if we do not calculate heat loss with the walls inside, only to the walls outside. Okay, I'll post some examples for you to practice, and let me know if there's some questions. For doors and windows, we have natural convection happening to the doors and windows, and it cools in the summer, in the winter, and heat in the summer. So windows and doors in the winter they cool the house, and in the summer they heat the house because they have glass and sometimes they're thin. So in the summertime probably you touch the door or you touch the window and it's kind of warm, so it's conducting heat to the inside. And the summer does the same. And there is the leakage is minor compared to transmission. So the air leakage, which is infiltration, is not that much, except if you don't have any kind of sealant around the door or windows. If it's very leaky, probably you will have a lot of infiltration. But mostly it's transmission. It's not much infiltration unless it's an old window. Doors are not as problematic as windows when it comes to heat loss because they're solid usually, and they do not get open and close as much as windows, and they don't have a lot of involved mechanism as windows. So that's something to keep. So to recap, we talked about building structure, heat loss calculation for one wall. Please go through the steps and tell me if it makes any sense, and I'll try to do that again live so you can ask some questions while I'll do it. And wall area calculation, you have to take out the window to get the net wall area, and I hope that was a little bit clear, or if not, I will try to reiterate. I will talk to air leakage and infiltration next week, and how do we calculate that and how do we counteract. And here's a practice problem for you. Please try to solve that and tell me if it makes sense. So we have a wall made out of brick. I gave you the R value and 2 layers of insulation with 0.35 each. So you will have your wall, 2 layers of insulation, R, R, R. So you will add all these ones. So R will equal, so you'll add all those 3 together. Then you'll get your U factor, which is 1 over R. This R that you got, you will divide by it and you get the U factor. You have the temperature difference, and you have the wall size and the R value for the window, which you can get also your U factor over here. And I want you to calculate the heat loss through the entire wall. And I promise this is going to be as complicated as it gets for this course. So look through the book and try to practice this a little bit. And the H22 book has have a nice elaborate example of an entire house about heat loss. But this is the basis. The basic idea is how to calculate heat loss through the wall, and usually we do the outside wall. Okay, I hope that makes sense, and please try to read chapter 2 and let me know if you have any questions. Thank you.